A capacitor consists of a number of equally spaced parallel conducting sheets. Alternate sheets connected together compose the positive plate, and the alternate sheets compose the negative plate as shown in the figure. If capital A is the area and D is the spacing between two adjacent sheets, the capacitance of the arrangement is. So here the arrangement is given. So we can see there are sheets placed parallel to each other, right? And there are simple n number of plates, and here these are connected to positive, right? And these plates connected to negative side. And then we want to find the equivalence capacitance of the system. Okay, here before I answer to this question, I would like to consider a system of parallel capacitors, actually a system of 4 parallel capacitors. So let me draw that first. Okay, I consider this is terminal A and this is terminal B. Here are the 4 capacitors. Each capacitance have the same area and same spacing, and also let's say each capacitance C, right? Okay, anyway, so here we can see this side of the capacitor is connected to A, and this side is B. So if I consider the potential here VA and here VB, so the potential difference across this one is this side VA and this is VB, right? Similarly here VA and this VB, right? Here VA and this VB, and here VA, potential here VA and the potential here VB. So each has the same potential difference, either VA minus VB or VB minus VA. If I consider VA is large, so like a positive side, so this is actually VA minus VB, right? Each has the same potential difference, and we can see each having one side same potential and the other side has the same potential. Okay, now we'll come to the actual problem. Now here I consider let's say our system have only 3 capacitors, I mean only these 3. In that case, now I consider this one. Now we have this capacitor, one is connected to here, let's say here A, and this is B. So here potential, whatever the potential A has, VA, and this one has the potential VB. And then when we have now this one capacitor and this is another capacitor, here one side is this one have VA and this one have VB. So if I consider only these 3 capacitors, then I have a system like this, right? So here this, if I consider this one side A and the other side B, and when I consider these two, it's another capacitor, one is having a potential VA, right, connected to A, the other one connected to B. So when we have 3 plates, we have 2 parallel capacitors, right? When we have 3 plates, we have 2 parallel capacitors. So if I consider 5, right, so up to here 1 2 3 4 5 capacitors. Similarly argument goes, and then we will obtain 1 2 3 4 parallel capacitors, right? So when we have 3, we have 2 parallel capacitors. When we have 5 plates, we have 4 parallel capacitors. Since in our system, in this arrangement, we have simple n number of plates, therefore we have n minus 1 number of uh, n-1 parallel capacitors, right? And each capacitor have cross-section area, sorry, each have the area capital A and the spacing D. So if I said the capacitance of one is C, so I can write C equals A epsilon naught over D, right? We consider this is in the air or vacuum, therefore epsilon naught, right? Okay, so now this is the capacitance of one capacitor, but now we have n number of n minus 1 number of parallel capacitors, each have the same value, because all here, if I consider this one, it also have C because same area and same D, right? So the equivalent capacitance of this arrangement is, we have C plus C plus C plus dot dot dot, right? We have n minus 1 terms because we have n minus 1 capacitors, right? Therefore the equivalent capacitance I can write, which is n minus 1 into C, right? And we know C is A epsilon naught over D, therefore we will get the answer, which is n minus 1 into A epsilon naught over D, right? So do we have some such answer? Yeah, here it is. So the answer is third one. Okay.